Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 6th video lecture. And today we want to start off with talking about the complex numbers. And so here's our definition for the complex numbers. So a complex number is an ordered pair AD such that A and B are both real numbers. We define two operations on complex numbers where A comma B and C comma D are elements of the complex numbers, so that script C is for complex numbers. And so our first operation is going to be addition. And the way that we define addition is that the complex number AB plus the complex number CD will be equal to the complex number A plus C, comma, B plus D. And that's the first operation, addition. And multiplication by AB times the complex number CD is going to be defined by being the complex number AC minus BD, comma, and then it's going to be AD plus BC. So that's going to be our definitions for addition between two complex numbers and addition between complex numbers and multiplication between complex numbers. And here I want to list a fact. It's an important fact. It says the complex numbers with the operations plus and multiplication defined above is a field with 0, 0 being the additive identity, and 1, 0 being the multiplicative identity. And so we want to prove those 11 field axioms are satisfied by the complex numbers with this addition and multiplication operations. Okay. So the first was that if you take two complex numbers and you add them, you're still getting complex numbers. So for those field axioms, remember what we have is three complex numbers. So we're going to let x be equal to AB, y be equal to CD, and z be equal to EF. And they are all complex numbers. 1. If we look at x plus y, that's going to be equal to AB plus CD. And by our definition of addition, this is A plus C, and then B plus D is the second coordinate, and that's a complex number. And the reason it's a complex number is what it takes to be a complex number is your ordered pair, where the first coordinate is a real number and the second coordinate is a real number. And A plus C is a real number because A is a real number and C is a real number. And B plus D is a real number because B is a real number and D is a real number by the definitions of X, Y being complex numbers. So that's the first thing that's satisfied. And then we want to look at commutativity. So X plus Y, what it's equal to AB plus CD, which is equal to A plus C, B plus D is the second coordinate. And then we can, because the real numbers are commutative, that's C plus A, and then D plus B, and that is equal to Y, or if you will, I'll rewrite this as CD plus AB, which equals to Y plus X. And that shows the commutativity of addition. The third thing that we want to show is the associativity. So if we look at X plus Y plus Z, that's equal to AB plus CD plus EF, and we can rewrite that as A plus C, and then B plus D, and then plus EF, and then that's equal to A plus C plus E, and then here's B plus D plus F, and actually I skipped a step there. Let me go back. Really, I should have written this, I'd like to write this differently. This is really equal to A plus B plus E, and here's, again, I'm going too fast. So, please forgive me. This is really A plus B, A plus C, comma, B plus D, plus E, F, which I will rewrite over here as the complex number A plus C plus E, comma, and then this would be B plus D plus F, which we can rewrite as, because the commutativity of the real numbers, is A plus C plus E, comma, and then B plus D plus F, which we will rewrite as, this is A, B plus the complex number C plus E, and then D plus F, which we can think of as AB plus, here this will be C, D plus E, F, which is the same thing as, this is X plus, this is Y plus Z. It's complex numbers. And so that is the associativity part. The next thing we want to show is the existence of the additive identity. And so here, for 4, if we'll say, let 0 be equal to 0, 0 in the complex numbers, then x plus 0 is equal to AB plus 0, 0, which is equal to A plus 0, B plus 0, and then A plus 0 as the first coordinate's just A, and B, which is equal to X. And that's what we wanted to show that the 0 in the complex numbers had. Okay? And then we want the additive inverse. So here, for additive inverse, we're going to define, define or let minus x be equal to minus a b, minus a minus b. Then, when you take the complex number x plus minus x is a complex number because a is a real number, so minus a is a real number. B is a real number, so minus b is a real number. So this is a coordinate tupole, if you will, of two real numbers. So here, when I add these two guys together, I get a, b plus minus a, comma, minus b, and then adding each coordinates, we get that this is a plus minus a, comma, and then b plus minus b, and then that's equal to 0, 0, which equals to the 0 element of the complex numbers. And then, sixthly, we want to look at multiplication. So if we take x times y, we want that to be a complex number. Well, x times y is going to be ab times cd. And so the way that that's defined is that's going to be ac minus bd, and then the second coordinate is going to be AD plus BC. That's its definition. And that's going to be a complex number because A and C are real numbers, so when you multiply them together, you get a real number. B and D are each real number, so when you multiply them together, you get a real number. If you take its inverse, additive inverse, that's a real number. And so when you add those two together, you get a real number. And the same thing is happening over here. A and D are real numbers, so you multiply them together, you get a real number. B and C are real numbers, so you multiply them together, and get a real number. Add them, two real numbers together, and you get a real number. And so we have a real number, comma, real number. That's a complex number. Okay, so that's what we have. And then we want to show that commutativity for multiplication. So x times y, which is equal to AB times CD, which is equal to AC minus BD, comma, and then AD plus BC, okay? So next, we want to look at y times x. Show that they're the same. Okay, this would be equal to CD times AB, and so that's going to be equal to CA, and then this would be minus DB, comma, and then it would be CB plus DA, is the same thing. These commute, so it's AC. These commute, BD, comma. This is BC plus AD. And then we rewrite that as AC minus BD, comma, and then commuting these two real numbers, that's AD plus BC, and that's what we get for y times x. So if you look here, what y times x is, and you look back to see what x times y is, at the bottom of the screen, you see that this formula for x times y and this form for y times x are the same. And so this is equal to x times y. So that shows the commutativity for multiplication. Now we want to show the associativity. 8 things. So here, note that x times y then times z will be equal to, well, this will be AC minus BD, this will x times y, and then here this is going to be AD plus BC, times, and here this is going to be EF, so you do this multiplication. And that's going to be equal to AC minus BD times E minus, it's going to be AD plus BC times F, comma, and the second coordinate is going to be AC minus BD times F, and then plus, it's going to be, I can have room, but I think I can get it in. It's AD plus BC times E. That's what it is. Then if we multiply this out, we get, this is ACE minus BDE minus ADF plus BCF, and then we're going to have ACF minus BDF plus ADE plus BCE. Okay. So that's what we have. And then I'm going to look at x times y times z, and that's going to be equal to AD times, if you will, y times z. That's going to be CD times EF, and that's going to be equal to, so it's A times B. I'm sorry, A comma B. That's a comma, A comma B. And then here, the way we do this multiplication here, it's C times E minus D times F. So the first coordinate is multiplied together minus the second coordinate is multiplied together. And then the second coordinate is CF minus D, plus DE. That's what it is. And so we can put these in parentheses. And so when we do this multiplication, it's going to be the tuple A times CE minus DF minus B times CF plus DE, comma, and then it's going to be A times CF plus DE plus it's going to be B times CE minus DF. And if we multiply this out, that's ACE minus ADE, where I'm distributing, minus BCF minus BDE. And I made a mistake here. This minus goes with this, so this should be a minus up here. Made a mistake. So make that correction. Yeah. And so that's what we have. Remember, this is a tuple. There's a comma. Here, this is going to be ACF plus ADE plus BCE minus BDF. And let's look at these and compare them. So ACE minus, well, this is a typo. ADF is what should be written right here. So this term and this term match up. Minus ADF and ADF here match up. So I made some typos here. Here's a BCF that's minus. Here's a BCF that's minus. A BDE and a BDE here. So the first coordinate of x times y then times z is the same thing as the first coordinate of x times the quantity y times z. And then here, this ACF matches with this ACF. This ADE here matches with this ADE here. Both plus. Here's a BCE. BCE here. And a BDF here, it's minus. And a BDF here, it's minus. So this is equal to, well, I'll write it this way. So that means that x times y times z is equal to x times y times z. And that proves the associativity for multiplication for the field axioms. The next thing is this existence of a multiplicative identity. So for 9, remember we're letting 1 be equal to 1, 0. And here, note that 1 times x will be equal to 1, 0 times a, b. Remember what we're trying to show is that this is equal to x. And so, by definition of multiplication here, it's 1 times a plus 0 times b, no, it's minus 0 times b, comma, then it's 1 times b, and then plus 0 times a, and then this is because of 1's multiplicative identity property for real numbers. This is a minus and 0 times something in the real numbers system is going to be 0. And then this is b plus 0, which equals to ab, which equals to x. And so that shows that 1 is the multiplicative identity. Next one's a little bit tougher to show the inverse existing. We want to show the multiplicative inverse exists. Now, here, before I do this, note AB being different from CD means that either A is different from C or B is, well, I guess when I say equal to, that A has to be C and B has to be equal to D. Okay? So for two complex numbers to be the same, their first coordinates have to be the same and their second coordinates have to be the same. That's what we're saying. So for them to be different, either the first coordinates are different or their second coordinates are different, or both are happening. Okay? So we're going to let x be equal to AB. So same generic complex numbers that's different from 0, 0. The additive identity. So that means, so either A is non-zero or B is non-zero. So that means that A squared plus B squared has to be greater than 0. For at least one of these is non-zero. If you square it, you get something that's positive in terms of the real number system, which is something proved. And it could be that both of them are positive, and you add them together and you get something greater than 0. So what we're going to define to be the multiplicative inverse of x, we're going to find 1 over x to be equal to A times A squared plus B squared, so that's non-zero, comma, minus B over A squared plus B squared. And what I got to show is when I multiply x times 1 over x, I get 1, which is 1, 0. So note, x times 1 over x is complex numbers. And this is a complex number. I hope that's clear, everybody. But this is a real number, and this is a real number. So this is equal to AB times A over A squared plus B squared, comma, minus B over A squared plus B squared. Okay, we do our multiplication between those two by the definition of what we're having for multiplication. So that's equal to A times A over A squared plus B squared minus, now it is B times minus B over A squared plus B squared, comma, okay, and then it's going to be A times minus B over A squared plus B squared plus, then it's going to be B times A over A squared plus B squared. I'm sorry, it's A squared, yeah, A squared plus B squared. That's right. Okay, that's right. And so that's equal to, this is A squared, and this is going to be minus a minus B squared. That means plus B squared over A squared plus B squared, comma. Here this is going to be minus AB plus AB, if you will, because of commutativity here, over A squared plus B squared. And then this is just 1, and this is 0. And that is the multiplicative inverse. I'm sorry, the multiplicative identity in the complex numbers. That's our 1. Okay. And then lastly, we need to show the distributive property. So we're going to look at x times y plus z, and we want to show that's equal to x times y plus x times z. Well, that's going to be equal to AB times, this was CD plus EF, add those together, that's equal to AB times, this was C plus E, and then D plus F is the second coordinate. We need to do this multiplication. Okay, and then this is going to be equal to, so it's A times C plus E minus, it's B times D plus F, comma, then it's going to be A times D plus F plus, it's going to be B times C plus E. Now, this is equal to AC plus AE, using the distributive property, minus BD minus BF. And then here, this is AD plus AF plus BC plus BE. So that's what we get. Now, if we look at x times y plus x times z, that's going to be equal to AB times CD plus AD times EF. If we do that multiplication, this is going to be AC minus BD, comma, and it's going to be AD plus BC plus, here this multiplication is going to yield AE minus BF, and then here we're going to have AF plus BE, and if we add these together, we add the coordinates together, and so here it's AC minus BD plus AE minus BF, comma, and then it's AD plus BC plus AF plus BE, it's an E. And that's what we have. And so if we compare these, so this was x times the quantity, y plus z. Here's an AC, AC. Here's an AE, AE. Here's a minus BD, and a minus BF, and a minus BF. They are the same. Here is an AD and an AD. Here's an AF and an AF. BC, BC, BE, BE. You see they're the same. So what that shows is that x times y plus z is equal to xy times xz. But those are equal to the same thing, same complex number. And thus we have shown that the complex numbers are a field. Okay, now I want to look at a theorem. It says, for any real numbers A and B, we have A0 plus B0 is equal to A plus B, comma, 0. And A0 times B0 is equal to A times B, 0. Okay, so this is just using our definitions of the two operations. So let's look at the proof. Let's let A and B be elements of R. Note that A comma 0 plus B comma 0 is equal to, well, it will be A plus B comma 0 plus 0, which is equal to A plus B comma 0, because 0 plus 0 is 0. Also, A0 times B0 is equal to, well, by the definition of multiplication, it would be A times B minus 0 times 0, comma, and then it would be A times 0 plus 0 times B, and that is indeed, I'm going to slip it in right here, that's AB comma 0. So that proves the statement. So that's all it said. But it's kind of nice to notice what we're proving here. So it's a very simple statement to prove, but what is it that we're saying? I'll write that over here. So this last statement states that the real numbers are a subfield of the complex numbers with or under the association of A from a real number is the same thing as A0 in a complex number. Okay? So that's association. Okay. The next thing is, when we talk about complex numbers, most of the time we do not see it in our beginning stages of mathematics as this tuple, the two-tuple A comma B, where A and B are both real. We normally see it as A plus BI. So here we're kind of looking at it in a different way to start off with, but we're going to relate that to the A plus BI way. But first of all, let's define that I. So I is going to be defined by 0, 1, and that's the element complex number. And the big property of I is that I squared is equal to minus 1. It's a fact. Here's the theorem. I squared equals to minus 1. And of course, minus 1 as a real number, that's going to be minus 1, 0. Okay? So that's our theorem through the association that's listed above. Proof of that is not so bad. Okay, so we're trying to show I squared is equal to minus 1. Well, note, so here's my proof. Note, I squared, which is equal to I times I, okay, and that would be equal to 0, 1 times 0, 1, and then that's going to be equal to 0 times 0 minus 1 times 1, comma, And then it's 0 times 1 plus 1 times 0. And that's equal to, this is minus 1 comma 0. And that is what we're defining to be minus 1 with the association to the real numbers. Okay, next we have a theorem that says that if A and B are real numbers, then we can have the A comma B, the complex number, can be rewritten as A plus BI. So let's look at that. So as proof, A plus BI is equal to, well, it would be equal to A0 plus B times I is equal to 0, 1. And we can think of B as B0. Well, that's a complex number, I should say. All right, so here I've written down A in its complex form, written down B in its complex form, and I in its complex form. And so this is equal to A0 plus, here I'm doing multiplication, so it's B times 0 minus 0 times 1. And then here it would be B times 1, and then plus 0 times 0. This is equal to A0 here plus, this is going to be 0, and this is going to be B, and then this is AB. And that's what we wanted to prove. Okay. So what that allows us to do is it allows us to work with the complex number AB in the form of A plus BI, where we can do multiplication and addition. Okay. So here, let me write this down. So we associate the complex number, complex field, A, B, with another representation that is the A plus BI, where we have addition of A plus BI plus C plus DI is going to be equal to A plus C plus B plus D times I, and A plus BI times, this times, C plus DI is going to be equal to AC minus BD plus, here it is AD plus BC times I. That's the association. That's what we had before. Okay? With the multiplication, the addition and multiplication with the A comma B representation. as a definition, if we let A and B be real numbers, and Z equal to A plus BI is a complex number, then the conjugate of Z is denoted by Z bar and given by Z bar is equal to A minus BI. We change the sign in front of the B part, the I part. A is called the real part. Of Z in the notation, Z is equal to A plus BI. And that is A equals to the real part of Z. And B equals to the, is called so B is called the imaginary part of Z. And denoted by B equals to the imaginary part of Z this way. Okay, let me at least write up a theorem and get maybe a part or two of it shown. But here's the theorem. It says, if Z and W are complex numbers, okay, then here's what we have. If you take Z plus W and then take its conjugate, that's the same thing as the conjugate of Z plus the conjugate of W. Part B, if you multiply Z times W and take its conjugate, that's going to be equal to Z conjugate times W conjugate. That's nice. C, Z plus its conjugate is equal to 2 times the real part of Z, and also Z, so that's one statement, Z minus Z conjugate is equal to 2 times the imaginary part of Z. It's 2 times I times the imaginary part of Z. So 2I times Z. And lastly, I can slip it in here, is that if you look at Z times its conjugate, Z times Z conjugate, that is a positive real number when Z is non-zero. So except when Z is 0. Okay, let us do at least one of these. is let, this is the proof, let Z and W be complex numbers. Okay. We want to show that Z plus W's conjugate is equal to Z conjugate plus W conjugate. Okay, so the way we'll do this is we'll start off with, we'll let Z be equal to A plus BI and W be equal to C plus DI, where A, B, C, and D are real numbers. This is W, not W conjugate. Then Z plus W conjugate is equal to, if you will, it is A plus BI plus C plus DI, the conjugate of that. So we do the addition first. And then that's going to be A plus C plus B plus D, I. We want to conjugate that. And that's going to be equal to A plus C minus B plus D times I. That's the conjugate. Okay. Now, Z conjugate plus W conjugate is equal to A minus BI plus C minus DI, which is equal to A plus C minus, it would be B plus D times I. So that does it. That shows that Z plus W conjugate is equal to Z conjugate plus W conjugate. And that's the first one shown. All right, ladies and gentlemen, we'll show the next three parts of this proof in video lecture 7. Thank you very much.